you. Okay, so the first time I think in my PhD I went to a conference. It was in group theory, and I started giving the talk, and then I stated some conjecture by Alex, and I misspelled your name. Then someone in the audience told me, how don't you know to spell your advisor's name? And then I had to explain, first of all, that I know how to spell it in Hebrew, not in English, and secondly, that you're not my advisor. I'm a proud student of Mathematicae, but I think this story says how much you influence even people who are not. Many people thought and still think I was your student, and I really attend. I mean, another thing. One of your jokes that I heard at least twice was that if you go to, I think, to Oxford, even the secretaries know what finite completion is. So I think it's also fair to say that in Jerusalem, even the secretaries know what expanders are, let's say, or many things in group theory, and certainly PhD students who are not your student know a lot about your stuff, and I took many classes of yours, and you were very supportive. Even though I was not a student, you were very supportive along the way in many different points in my career, and I'm very grateful for that. And okay, so I'm going to talk about a work I've done with Michael Magee and Doron Puder from last year. So I'm going to, this is a work about random hyperbolic surfaces, random covers of hyperbolic surfaces, but I'm not going to speak much about hyperbolic structure. It will be mostly about, you'll see, but, and the talk, so it has three parts. I'm going to start by talking about graphs, and only then I will switch to surfaces, because in these two theories of spectral gaps in random graphs and random surfaces are very much intertwined. Sometimes graphs, the theories and conjectures in graphs came first, sometimes surfaces came first, and many of the ideas are now common. And then in the last part, I will say a few words as much as time permits about the proof. It will be on the whiteboard. Okay, so let me start with graphs. So okay, let's put this here. Okay, so we start with much of what I'm going to say was already said this week, so I'll be a bit quick about graphs. So let's say that G is a d-regular graph on n vertices. So it has the spectrum of the graph, or the adjacency matrix. We have n eigenvalues. It's an n by n matrix. It's symmetric. All the eigenvalues are real. The largest eigenvalue, which I denote by lambda naught, is d. And the difference between lambda 1 and lambda naught, so yeah, so lambda naught minus lambda 1, this is the spectral gap. And it measures the connectivity of the graph, how much the random walk converges quickly to the uniform, and so on. And the question is how much the spectral graph can be, how large can the spectral gap be? The larger it is, the more connected the graph is. And the famous conjecture, a famous theorem by Laplacian is that lambda 1 is at least the spectral radius of the d-regular tree, which I denote by Td, minus O of, let's say, 1 over log n. So n is the number of vertices of the graph. And by Kesten, we know that the spectral radius of the d-regular tree is this number we all know, many of us know, 2 square root of d minus 1. Okay, and then there are two natural questions that come up when you look at this bound, whether this is tight. Okay, the first question is whether this is tight. So is it true that as n tends to infinity? Of course, for small graphs you can get better than that. I mean, but when n is very large, can you obtain something which can you get anything better than this bound, or is this bound tight? And second question, this was actually a conjecture by Noga Alon at 86, what is the typical behavior if you look at random graphs? Okay, so this was mentioned several times here. I mean, actually, the first question, the first answer I think came even before roughly the same year as the bound. So the answer is yes. I mean, this is tight, right? So the answer is yes. These were the constructions, the explicit constructions by Lubotzky, Philip, and Sarnak, and Modroulis. To be fair, these were not, so this is only works for certain values of D, not for all these. But then the second answer, actually, the first time we knew that this is tight for every D came from the answer to the second question, which is by Friedman. So Friedman, in a way, showed that random D-regular graphs are nearly optimal expanders, namely the probability that lambda 1, the second, so lambda 1 here is the second eigenvalue. It's at most 2 square root of D minus 1 plus epsilon, for any epsilon, tends to 1 as n tends to infinity. So random graphs are nearly optimal expanders. And by the way, so in this talk, I'm not talking about, I don't distinguish between strictly Ramanujan, where the second eigenvalue is strictly less than that, or plus epsilon, basically because this is what we know for surfaces, so I'm not making this distinction. So for me this is tight, right? It means that the bound is tight, and it's also the right bound for random graphs. Okay, and I do want to mention, despite what I just said, that we now understand much more. We understand exactly by this recent incredible result by Huang, McKenzie, and Yao from about a year and a half ago. We know exactly what the distribution is of this second eigenvalue. It looks like Petty-Widom, and so we know a lot about, let's say, just we know a precise or relatively precise description of the distribution of lambda 1 for the regular graphs. Okay, so what did Friedman actually prove? What did he actually show? So I'm going to speak about one particular model of his. He talked about several models, but they're all, I mean, the proof is roughly the same. And for simplicity, I'm going to only stick to D equals 4, so 4 regular graphs. So first of all, how do you generate, one of the main models he worked with, how to generate a 4 regular graph. So you generate a 4 regular graph on n vertices by taking 2 permutations in a symmetric group on n elements. And as an example, okay. Yeah, thanks. Yeah, so let's assume that sigma bar is 1, 2, 3. So I'm just going to do 1 goes to 2, 1 goes to 2, 2 goes to 3, and 3 goes to 1. And tau, the other permutation, sends 1 to itself and exchanges 2 and 3. So there I hope you can all see, I got a 4 regular graph from 2 permutations. And the model that Friedman uses is to take uniformly random, independent 2 permutations, and you get some random 4 regular graph. Okay, so the adjacency matrix of this graph is simply you sum these 2 permutations, sigma and tau, and their inverses as permutation matrices. So these are n by n matrices. This is the adjacency matrix. Now again, as was mentioned in some of the other talks this week, we need to get rid of the trivial eigenvalue, this lambda naught, which is D. This always comes from the all one vector. So we want to get rid of it, so what we do is just restrict ourselves to the orthogonal space. And the reason I denoted these permutations with a bar, because I really want to look at their image in the orthogonal space of all the vectors that sum up to 0. And so I denoted by sigma tau and the adjacency matrix by AN without the bar. And this is now an n minus 1 on n minus 1 matrix. No, it just, I mean, in this model I allow it. But there was a constant proportion where you don't have, where the graph is simple, you don't get, for constant proportion of the graphs, it's simple, and on this proportion you get uniform distribution, and everything you prove here is also true for the, you get it for free for the simple, uniformly random simple graph. Okay, so so Friedman, what he actually showed was that, so if you look at the operator norm of this matrix, right, this n minus 1 by times n minus 1 matrix, it converges in probability as n tends to infinity to square root of d minus 1. Okay, so this is another way to view this result. Now we have the yeah, okay, so we have a parallel picture for the Cayley graph of the free group of two generators. Again, two generators because we have two permutations in this setting where d equals 4. And we can also look at the adjacency operator on the Cayley graph of the free group. And the adjacency operator is simply UA plus UB plus UA inverse plus UB inverse, where UA is just the regular representation of A, so lambda. So lambda is just the regular representation on L2 functions on the group. Okay, so this is very simple. You just think about functions that are defined on the vertices of the tree. And okay, they're in L2. And then UA, you just look at every vertex and you ask what is the value of the function on the vertex to the right, right? And UB, you look at the vertex on top, and then you just sum these functions, and you look at the spectrum of this. So in this perspective, I'm going to write Friedman result yet another time. What Friedman showed is that if you look at, again, sigma plus tau plus sigma inverse plus tau inverse, this matrix, it converges in the operator norm. The operator norm converges n tends to infinity to the same expression, but now you look at the regular representation of the free group. Okay, so it's just another way to frame this theorem. Okay, so this is what he proved. Now I want to get to mention one nice extension of his conjecture. It will be related also to what I'm going to say about surfaces. So roughly the same time that he proved this conjecture, he also conjectured that the same phenomena, what Alon conjectured, not Alon conjectured, also holds for random covers, or what some people call lifts, random covers of any finite graph. So I want to, again, this was also explained in, I think in your talk, also in other talks, what is this model of random covers of graphs. So, so you start with a graph, let's say, so, okay, I'm not sure you can see. Okay, so this is the model, you take any graph. Now there are several ways to describe this model. One way is to just take, so this is my graph, I pick a spanning tree and I look at all the remaining edges. And now to get a tree cover, I take 3 copies of the spanning tree, and for every remaining edges, I take at random a permutation that tells me how to draw it in the cover. So for example, let's take here another example. So let's say that my pink permutation is 1, 2, 3. So I'll go from 1 to 2, from 2 to 3, and from 3 to 1. And let's say that the green permutation is 2, 3 as before. So now 1 is a fixed point, which is going to be like that, and 2 and 3 is a transposition. Okay, so I got a covering. So Friedman conjectured that in this model, again, we have roughly the same thing.
This
Okay, so it doesn't depend, right, thank you. It doesn't depend all on the spanning tree. I could also just take, this is a relatively easy exercise. It doesn't depend on the spanning tree. I could also do the same trick for all the edges uniformly. I don't even have to do.
And you get the same distribution.
I get the same distribution. This is actually equivalent to just taking uniformly random homomorphism from the fundamental group of my graph to Sn. Okay, it's the same thing. Yeah, and yeah, and I should say that we also have the Alon-Bopana. We have an analog of Alon-Bopana, which was proven by Greenberg, a student of Alex, I think. Okay, and here is what Friedman conjectured in 03. It was later proved by Bordenave and Collins in 2019. So what they showed is that the lambda 1 G, and now this is not the second eigenvalue precisely. This is, I wrote here a star, which means that this is a relative highest eigenvalue of the cover. This should be, so it should be a cover. Let's denote by n. So Gn is the cover. This is okay. Gn is the cover, the n cover. Lambda 1 star is a relative spectral. It's the relative spectral graph because the problem is that all the eigenvalues of this graph are inherited by the cover. I just take, I have some eigenvalue. It means that there is an eigenfunction, some function defined on the vertices. I can lift it up to a function on this with the same eigenvalue. So I cannot get rid of the old eigenvalues, but I can hope to bound the newest eigenvalue. And what they showed is that what Bordenave and Collins proved is that its relative eigenvalue is at least so it converges in probability as n tends to infinity to the spectral radius of the universal covering tree of this graph. Okay, so this number, when the graph is regular, this is going to be 2 square root of d minus 1. For general graphs, it will be another number. Okay, and this is based on, okay, this is the result that appears in the title of the theory of the paper by Bordenave and Collins, but this is not really the remarkable thing they proved. Okay, I mean, this follows from the main theorem, the real main theorem of this paper, by the observation that, so they had this observation, it's pretty simple, that you can decode, so remember in Friedman's theorem we were able to decode the adjacency matrix of the random irregular graph by a sum of permutations. And this is true also in this model. It turns out that you can encode the adjacency matrix of this n cover by some polynomials in these two permutations, or in general in these permutations that you generate by which you generate the random cover.
Non-commutative.
Hmm?
Non-commutative.
It's first of all, it's non-commutative. Non-commutative from, and if you want to be precise, even the coefficients need to be matrices, but so you can encode it in polynomials, and here is what they really proved, and this is a remarkable result. They showed that for every polynomial, and now I will not say it with the matrix coefficients. So let's say imagine in this case a polynomial non-commutative with 4 generators, with 4 variables, sorry. So for every such polynomial, if you look at P and you plug in your 2 permutations and their inverses, and you look at the operator norm, it converges in probability to the same thing you get for the regular representation, what we had before.
What is a free group?
In the free group, yes. Okay, so remember, Friedman result was a remarkable breakthrough. It took more than 100 pages to prove this result just for one polynomial. And they prove it for every polynomial. So it means that you can take any polynomial in your permutations. By the way, this is of course, without, this is again, it's permutations, but without the, in the subspace which is orthogonal to the all one vectors. But so for every polynomial you take, you look at for random permutations, the largest eigenvalue will be roughly, or the operator norm will be roughly what you get for the regular representation of the free group. And this phenomenon now has the name of strong convergence. So this phenomenon, that this is true for any non-commutative polynomial, we now call it the strong convergence of random permutation representations. So this is, remember, I mean, this is like we took actually random. We just took I told you that sigma and tau are just this is like a random homomorphism from the free group to Sn. So this is a random permutation representation of the free group. It converges strongly to its regular representation.
Is there any similar result for random regular representations for some, I don't know.
So what is random? Oh, regular. Oh, yeah. Yes. Yeah. So first of all, for random regular representation, you can, let's say, to unitary matrices, you can look again at. Instead of looking at two random permutations, you could look at two random unitary matrices, and this is true. This is actually appeared before. It's a result of Collins and Mallet.
No, I'm just talking about not by using permutation. Yes, you consider this covering, not the regular covering. Yes, you consider general covering. Is it possible?
If you just want regular covers.
Yeah, regular covers.
This I don't know.
Simple, for example.
No, this I don't know. I don't know if we. It's a much more restricted set. I don't know. But for the question I thought you asked, yeah, there is,
Okay.
I mean, actually, if you replace permutations by unitary matrices, this is easier. Now everything is much easier. I'm going to tell you about it soon, but this was first proved in 2014 by Collins and Mallet for unitaries. Okay, so yeah, this was remarkable, and then came an even more remarkable, not more, another remarkable thing. I don't want to. Which was the proof, a very short proof of all this story by Chen, Garza Vargas, Trop, and Van Handel. So I think they came up with it 2 years ago. It was published in the Annals last year. So this is a much simpler proof that proves all these results I've told you so far about permutations and also about unitaries actually. This is the closest one can hope for. This is like probably the proof from the book of this of Friedman's theorem. So it's a much simpler proof. It requires some very, I mean, I'm going to say a bit more in the end of my talk about what this method requires as input, but it requires very, Ramon likes to call it soft input. You don't need to know much to understand much about the random model you're working with. You need to understand only a little bit. Okay, so hopefully I will say more about it at the end.
I mean, you should have said that in free probability theory, the reason strong convergence is convergence in density is Voitovescu.
Right. Yeah. It's strong. Okay. Right. So strong convergence is in contrast to weak convergence, which is the notion that is related to what Voitovescu did, which means that here we actually look at operator norm. Weak convergence just said that the measures converge. This is like more like Benjamin Schramm convergence. This is the kind of this is the spirit of weak convergence. Okay. So are there any questions? Because I'm going to talk about surfaces now.
The input here, the sigma and tau are random, random, or like you assume different, like a more general model?
So here, what I wrote here, the input they need is that, I mean, basically, roughly, it's enough to know that if you take two random permutations, uniform random permutation, and W is any word in the free group, and you look at the trace of this permutation, or in other words, the number of fixed points of this random permutation, you need to know that, or you were supposed to know in this, I mean, you need to know for this work that this expected number of fixed points is a rational function in N, like Yuta mentioned this morning, and you need to know something a bit more about this. I will say more about it at the end.
For here, the sigma and tau are completely free. They don't have to satisfy.
No, they don't. No, they're free. This is important. It makes things much easier. Yeah.
It's not related to the relations they might
No. They only no.
Free
no.
variable.
Yeah, free variable. Any other question? Okay, so let's move on to surfaces. Okay, so surfaces. So now I'm going to talk about closed hyperbolic surface of genus at least two. As you'll see, I will be mostly interested in just the fact that I'm just going to look at is it as a topological space and fundamental group. But the hyperbolic structure. Okay, so first of all, sigma. I mean, it comes from hyperbolic surface, means that you can think of it as coming from some quotient of the hyperbolic plane by some uniform lattice. And the Laplacian operator on the surface, the Laplacian operator on the hyperbolic plane descends to sigma, and you can extend it to be defined on L2 functions. And it's classical fact that the spectrum of the Laplacian on a closed surface is discrete. You get an infinite discrete spectrum, and lambda n tends to infinity as n tends to infinity. And again, we have this phenomenon, right, just like graphs. But by the way, I mean, I should say that you should think of regular graphs are like they have constant curvature, because on every vertex you see the same degree. This is like hyperbolic surfaces have a constant curvature, and as in surfaces. As in graphs, where you saw from Friedman results, the regularity is not really important. Also here, the hyperbolicity is not really important. But anyway, so just like in graphs, we have the spectral gap, which is this is the spectral gap. I mean, in this case, this is just lambda 1, or the difference, which is also the difference between lambda 1 and lambda naught. Lambda naught, by the way, is 0. This is the constant function on the surface. And the spectral gap, again, measures connectivity. It measures how fast the geodesic flow converges, or how, if you cut a surface into two different surfaces, how long the cutting curve needs to be, and so on. So again, the natural question is how large the spectral gap can be. And the analog of Fallon-Boppana, which came much earlier, is due to Huber from '74, and he showed again that this lambda 1 is now we change the direction, because we look at the Laplacian. It's at most lambda 1 of the hyperbolic plane, so the bottom of the spectrum of the Laplacian on the hyperbolic plane, plus O of 1 over log G, something like that. So G is the genus of the surface, and lambda 1 of the hyperbolic plane is 1/4. Okay, and this is due to Selbel.
Everything.
Okay, and now, so again, we have the same question as in graphs. Is this tight? So do we have a natural upper bound? So again, I mean, I think people early on knew how to construct surfaces of small genus where this is where the spectral gap is strictly larger than 1/4. But is it tight when the genus tends to infinity? This is one question which was raised by Puder. I think he conjectured that it isn't, and then he conjectured that it is. But the last conjecture was that it is tight. And then again, there's the other question, the analog of Alon's conjecture. What is the typical behavior for random surfaces? Okay, so now I should just say that unlike in for graphs, we don't have proven constructions, explicit constructions. The closest thing we have is the Selbel's conjecture. If it's true, it should give an explicit construction.
Selbel's conjecture is that there is an explicit construction on it.
But not for closed surfaces, not for closed surfaces. But yeah, I mean, then you can, basically yes.
It's not that they exist, it's specific guys
Yeah,
must
yeah,
satisfy
yeah.
it, which is useful, because that's what we're interested in.
Okay, so the model I'm going to talk about mostly is covers of surfaces. So it will be very similar to covers of graphs. And so again, I want to simplify things. We'll just focus on genus 2. By the way, genus 1 is a completely different picture. It's not it doesn't have a hyperbolic structure. Also, many of the things I'm going to tell you do not work for genus 1. This is a very different creature. So we start the simplest case is genus 2.
I think it's the same in graphs if you take two regular.
Right, yeah, in a sense, right. Yeah, two regular, yeah, it doesn't work. Okay, so this is our surface. And now I'm going to use this combinatorial description, right? If this is my surface, I drew some lines here in advance. And if you cut along these lines, if you have this base point, if you cut along these lines, what you get is an octagon, topological octagon. And to get it back, you just glue together these pairs, this A to this A, and so on. You can glue and get back the genus 2 surface. And okay, now what is the model for an n cover of the surface? So I'm just going to take n copies of this octagon, and thankfully I can do it. I can really take n copies of this duplicate, right? Duplicates. No, this is a mistake. No, sorry. No, I can't. I'm not sure. Okay, once it. Yeah. So here, duplicate. I'm going to do it n times. Okay. Okay, so I have here 1, 2, and up to n. Okay, so I have n copies of this. I call them 1 to n, and now I want to glue them together. So what I'm going to do is to take 4 permutations. I call them so sigma A, sigma B, sigma C, and sigma D from the symmetric group. And this should tell me, and I'm going to use it to glue them together. So if sigma A sends 1 to 2, I'm going to take this A, which is the outgoing A of 1, and glue it to the incoming A of 2. Okay, so I'm going to glue this edge to this edge and so on. And I glue everything together and I get a surface which is, okay, I'm going to get a topological surface. What's the problem? This is not enough to get a cover. Right? It's not enough because where's the problem? So it's not connected, it's still a cover. The problem is at the vertex, at this vertex, right? I mean, generally, if I just glue it without paying attention, I could see that along this point, around this point, this is not going to be a cover. I mean, the local picture here will not be the same if I just glue them without further restrictions. What I want is also, if I go around every vertex, what I will see is the same picture over here, right? So for this, I need the extra condition. So I want to pick 4 permutations such that the product of commutators is 1. Okay, as a permutation. This is in the permutation in the symmetric group. This guarantees that around every vertex I'm going to see the same picture as there. Okay, and equivalently, this is just equivalent to saying that so what I do equivalently is choose a random homomorphism from the fundamental group of my surface, which is just, of course, the group generated by 4 elements with exactly the relation that we had, the product of 2 commutators, to the symmetric group. Okay? So equivalently, again, I just take I take a uniformly random homomorphism from my fundamental group to Sn. And this, in general, we have these. So we use this standard or classical classification of covering spaces by deck transformations. So in our case, this is just the set of homomorphisms from the fundamental group to Sn is in 1-to-1 correspondence with n covers of the surface, and here I need to specify with a fiber labeled 1 to n. I mean, to make this precise. Okay. Question? No. Okay, so
Topological covers, not the generalized branched covers.
no, these are topological covers, right? And if I start with hyperbolic surface, I can also pull its matrix, yeah, the structure, the hyperbolic structure. So, yeah, so I also get random hyperbolic surface if I start with an hyperbolic surface. Okay, so how now remember we want to. The goal was to again look at the we studied the spectral gap of these surfaces. And now it is much less clear. In Friedman's theorem, it was very, very easy and direct how to connect these random permutations to the spectral gap. This was just another way to frame the same question. Here it's more involved, and this was one of the important observations of. One of the important observations of Will Hyde and Michael Magee in 23, which they understood how to encode the first eigenvalue. Now again, the first eigenvalue, this is relative again. If you have a cover of a surface, again, you have all the old eigenvalues. Again, they are inherited by the cover. You cannot get rid of them. So the best thing you can hope for is to bound the smallest new eigenvalue, which is what I call the relative lambda 1. And they were able to encode it again in polynomials in the permutation. So basically what they showed is that lambda 1 of the relative new eigenvalue, the smallest new eigenvalue, converges to the bottom of the spectrum of edge of the hyperbolic plane as n tends to infinity if you look at okay, you have the pi 1 of the surface, you have the homomorphism you choose to Sn, and then you look from Sn as before, you generate the matrix in the n minus 1 by n minus 1 matrix. So they show that this is true if and only if, not infinite, if this sequence of homomorphisms converges strongly to the regular representation of the fundamental group. Okay, so basically they were able to encode this problem to translate it to a problem about strong convergence of these random permutations. Now, what's the problem? I mean, so now why is it not immediate to prove Buzer's conjecture that you get that you can obtain these surfaces which get the bound of 1/4, which approximate the bound of 1/4. The problem is that, of course, the fundamental group of a surface is not free. So we cannot apply, we don't have this Bordunov-Collins result, right? We don't have this full convergence. We didn't have this convergence in 23. So how did they go around it? Because actually they did prove, in the same paper, they did prove that Buzer's conjecture was true. So they proved that yes. And so remember the question was whether whether the Buzer bound is tight, whether you can reach when a genus whether you can get surfaces of arbitrarily large genus where spectral gap approximates 1/4. And the answer is yes. And what they did was to start with to take sigma, which is non-compact with cusps. And then the fundamental group is free. Okay, so pi 1 is free.
Of course, in the theorem above, you need the base guy not to have a bad idea.
Right, yeah, that's true. Yeah, you should start, right, because we cannot get rid of the old spectrum. We need to start with some surface, it can be small, with it should be with cusp, so the fundamental group is free, and also no small eigenvalues. But this was known before. Such surfaces were known. And then they used, I mean, of course, this is much harder than the way I describe it, but they used Bordenave and Collins to show that you have, and this result from before, that you have covers with, okay, good covers, let's say. You get good covers, or random covers random covers are good, they are approximate 1/4. This is not a compact surface, but then you can use some compactification where you glue together different cusps and make it a compact, and you don't lose much in the spectral radius to prove Buzer's conjecture.
Cusp here, you mean just missing points?
Yeah, missing points, but it also goes into account. I mean, then the hyperbolic structure is different, right? I mean,
As a result of Berger and some, maybe.
I mean, it's
Dodgek.
compactification.
Yeah.
Yeah, I think it also
Maybe Dodgek, I don't know.
Yeah, yeah.
He's right.
I think there were several
You can ask
independent.
him, he's right there.
Okay, now did I want to say anything? Okay. Okay, this was the first question. This was a remarkable result, also announced. And then it remained to understand what happens for typical surfaces. This is the second question. If you look at random hyperbolic surfaces of, let's say, of a given genus or a genus going to infinity, do they usually look like the spectral gap usually approximates 1/4? And now the first result in this direction was another remarkable work of Nalini Anantaraman and Laura Monk, which appeared early last year. They worked in the Weil-Peterson model. Double S? Okay. Or double T? Okay. Okay, it's a different model. I'm not going to go into it, but it's in a sense it's a very natural model. It gives you a precise measure on all the possible hyperbolic structures of a given genus, and they show that the probability that you get very close to quarter gets very tends to 1 as the genus tends to infinity.
Actually, you should give them also credit for the first people to really understand Friedman.
Yeah, that's true.
So you see the
Yeah, that's true. I mean, so actually the method here is they really seem like they really understood Friedman's original proof, and they followed very roughly his proof. And in the spirit of Friedman's paper, this is also hundreds of pages long.
And by the way, in that field, 100 pages is acceptable, unlike in combinatorics. So that's the problem.
Well, no one reads the. Yeah.
I mean, the fact, in some fields, people boast how long their papers are.
Yeah, and then we, together with Michael and Ramon, we proved it in the random cover model.
How many pages?
34. Okay, it's also based on the previous works, but yeah. So we showed basically that for random covers models, you can start with a surface which is compact, so you don't need to use cusps and then compactify. You can start with a surface which is compact and obtain that the random cover has a spectral gap almost 1/4.
You're using Lauder and Magee.
No, we're using our work of Michael and myself.
Because there is an in-between work which avoided cutting the cusps by
Right.
surface groups.
Yeah, but then the random model is very right. But then it's a very twisted. Yeah, that's true.
Sorry, can you comment how you formally define this random cover model? So you have this like monodromy representation. Yes, you.
So this is what I said before. I mean, this is this picture. Right? Yeah, it's very precise.
Yeah. So you just choose permutation and check this condition if it's succeeds.
Yeah. So
you mean,
take it uniformly
uniformly
random
random?
on this set. This is a finite set. Take a uniformly random element of this set.
Okay.
But so I guess I'm asking you, for which groups do we know now that you have strong convergence into the symmetric group.
Okay, so just, okay, 1 minute, I just want to say that we now, I mean, the way we go about it, I mean, of course, you could have guessed if you followed this talk so far. How do we prove it? We prove actually that the strong convergence that was known for free groups also holds for surface groups. This is the main result of our paper. That again, you choose these uniformly random permutation representations of the fundamental group of a surface of genus at least 2. And again, you look at this, what happens in this n-1 dimensional representation, and we show that it converges strongly to the regular representation of the fundamental group of the surface.
So you're saying that Hide and Magee and Lauder went through some right-angle triangle groups?
What they did is they show that so they use different embeddings of okay, they sent the generators of the surface group into very long words in the free group, and then they use the strong convergence of the free group to say that they have approximate strong convergence in the surface group. So it still goes through Bordenave Collins. Yeah. So again, this means that again for any polynomial in permutations which satisfy this relation of the product of commutators, the slopes, the operator norm converging probability to the operator norm of the same polynomial in the regular representation.
And so in your theorem, what kind of group can I replace the surface group by?
Okay, yeah. So we don't know much about this. I mean, certainly, I mean there are several different questions you can ask about random or explicit.
Just like a hyperbolic three-manifold group.
No, of course we don't know it about it. We don't. I mean, this would be yeah. I mean, this of course would be incredible.
So
but
at this point, it's just surface.
surface groups, we have some. Now it's also known for free products of finite groups.
You don't know it for any hyperbolic three manifold?
For any, no.
One will
I mean, the entire question is still open for three hyperbolic groups. I mean, we don't know that the analog question about spectral gaps of hyperbolic three manifolds is whether you can approach it. This is still open. Yeah. Okay, whether you can approach the spectral gap of the hyperbolic three manifold. Three space. Okay. Okay. So this is the result. I want to say a few words about the proof. I also know that some of you need to go to another talk. But I want to use the board now.
שם כזה לכבות הכל.
Okay. Oh, I missed this. You see, Michael? So it's done.
ירדתי למטה ועוד לא סיימו את השם.
Okay, so this is part 3 of my short. I want to say some words about the proof of this result. So I want to start with the polynomial method. Again, this is due to Vargas, Drop, and Van Handel. So remember that what we want to prove is that, so remember that we have this AN, which is just, this is an n-1 matrix. It's symmetric, and we have the eigenvalues, which I'll denote by, these are lambda 1, lambda 2 up to lambda n-1, and our goal is to show that these are random permutations, and we want to show that the probability that the maximal, let's say, absolute value of the eigenvalue is at most is strictly more than, in this case, 2 square root of d minus 1 is just 2 square root of 3 plus epsilon. We want to show that this goes to 0 as n goes to infinity. And the way you want to show it, I mean, one way you could hope to show it is to look at, okay, so this is minus 2 square root of 3, 2 square root of 3. Let's say you have some function. Let's say h is some smooth function. It doesn't have to be smooth, but we will. Which looks like that. So it is 0 between in the Ramanujan interval, and it's going to be 1 outside the Ramanujan interval plus epsilon. And so it is enough to show that the expected value of the sum of on all the eigenvalues of h of lambda I. Okay, what do we need to show? That the sum is, I mean, if it's 1, it's already a problem, right? If it's 1, you already have a negative value outside the Ramanujan interval. So we want to show that this is at most, this is small O of 1. Okay, it goes to 0, this expected value. Now, if we replace now, how do we do it? So we can, I mean, we don't have any direct access to a smooth function on the eigenvalues. What we do have access is to polynomials. So if we replace h by any polynomial, let's call it p, we can analyze the expected value of, again, the sum of p of lambda I. Okay, where does this come from? So this comes from relatively easy and results of Nika. So let's assume that, I mean, I'll just show it on just simple powers on the basis, and then it will follow for all polynomials. So if p of lambda, the polynomial is just lambda to the L, then what is the, then p of this, then the sum of p of lambda I, right? This is just the sum of lambda I to the L, or in other words, this is just the trace of an to the L, right? It's just these are the eigenvalues of an to the L, and remember an is just this sum of permutations. And now I open it, what I get is the sum of all the words in A, B to the L. So just, these are formal words in A plus minus 1 or B plus minus 1 to the L of the trace of my word in sigma and tau. And the trace of a permutation matrix is number of fixed points, right? So this is just the number of fixed points of W of sigma and tau. And because I'm looking here at permutations that are only the permutation restricted to the subset which is orthogonal to the all ones, I need to subtract 1. This is what it translates to. Okay, this is some basic thing, and then now I don't just want to look at the sum for particular permutations, I want to look at the expectation, so I'm just going to add here expectation, and then I get this expectation. Of course, I need expectation along the way.
This AN is the image of this under the standard representation, right?
Sorry?
This AN is the image of this thing under the standard representation.
Yeah, standard n minus 1, yeah.
Not so arbitrary.
Yeah, standard n minus 1 representation of the symmetrical pair. N minus 1 dimensional representation, yeah. Right, and here what we need, so this morning we heard that we have some information about it, but we don't really need only the very basic information about this, which was already known to Nika. So Nika, in '94, he proved two stuff. He showed first of all that E of the expected value of this number of fixed points of W sigma tau is a rational function, basically. So this means that you can write an expression of a polynomial divided by a polynomial, and this function coincides with this polynomial for every n, for every large enough n, but less. This is the first thing he showed. The second thing is that this expectation of number of fixed points minus 1. So we have three options. I mean, of course, if W is just the identity, I mean, if it cancels until you get, if it reduces to the identity, then you just get n minus 1 fixed points, of course. You have n fixed points, so minus 1. If W is a proper power, you basically get, I would just write as roughly 1 fixed point plus of 1 over n. Remember, this is, I subtracted 1, so this means that you have at least 2 fixed points in a random permutation. And otherwise, for all non-powers, you get O, so this is big O of 1 over n. This is also big O of 1 over n. Okay, this is basically the main point of Nika's result. Okay, and then okay, by the way, this is also I would say this rational function is tamed. So we know more about this rational function. It has we know the degrees and so on of these two polynomials. We have quite a lot of information. So the corollary from this is that again, if I go back to the polynomials, that for any polynomial, no, k at least 2. K equals 1 is the non-power. I mean, yeah, I mean,
A word which is a power of some
a proper power of another word.
Proper power of another.
Yeah.
Okay.
So because now every polynomial is a sum of these, is a linear combination of this, what we get is that for any polynomial we can write the following. We can write, we can look at this expected value of, so the expected value of the sum of the values of the polynomial in the eigenvalues, right? And then we subtract what we get from the word that converge to 1, which I would call it nu 0 of p, some value. And then I subtract the words that are what I get from these proper powers, which are denoted by mu 1. And this difference is of order 1 over n at most. Yeah. Yeah, okay. Everyone who wants to go to the Lubotzky talk, I'm not going to be insulted, please. Yeah, I need 2 more minutes. It's fine?
Yeah, I'm okay with it, but if someone needs to go to the other one, okay, perfect.
Okay, so, yeah, okay, so we know this. Okay, so we have some functional, these are the functional, these are just the values we get from these, from this theory, we get some values about, on these two expressions. And we actually know a lot about these values. And the crux of the polynomial method, which was developed in this paper by the 4 people I mentioned before, is that they take split properties, this property, So they take, this is their input, and also some estimates on the exponential growth of proper powers. So I mean the exponential growth rate. So how many proper powers you get when you, on a random walk in the free group? Okay, this is basically the question. From these three inputs, you apply some 150-year-old inequalities on polynomials due to Chebyshev, or and Markov again, the same Markov that Peter mentioned in the stuff.
Spelled that way.
Hmm? Yeah, spelled there, yeah. This is how these the polynomial people in that space actually. They show that you can get the same thing for, this is true, so you get the same estimate for any smooth function. And because we know we know good properties of this, we know that these two, basically these two functionals are extendable. They extend to all smooth functions, and they are both zero if the smooth function is zero in the Ramanujan interval. So if the smooth function vanishes on the interval, then these two functionals are zero, and therefore what you get, this is just zero, you get exactly what you want. The expected value of the smooth function evaluated at the eigenvalue is O of 1 over n. Now, of course, this is here's where the crux lies, but this is only a 2-page proof. This is pretty amazing. So this is roughly the story, and I'm out of time. I just want to say what happens in surface groups. What's the problem? So in surface groups, so we have these very rough 3 things we need as input. Now, the first thing is that, okay, let's start with the second thing, is that we have this behavior of the expected number of fixed points. So I can do the same in surface groups. Look at, again, random homomorphism of surface groups, and then evaluate an element of the surface groups. Look at the image. This also gives me a random permutation. And it turns out that we have exactly the same result. So for surface groups, we have this. This is a result of Michael and myself from a few years ago. This is V. Yeah. We have that. This we didn't have before, the exponential growth rate of proper powers, but we proved it in our paper. But the main issue was that this is just not true. Okay, we don't have this rational. This is just not true in the surface groups. It's not even analytical. If we try to look at this function, it's not even an analytic in n. And so what we had to do is to show that there is a still good control on this, and make this method more flexible so that it can works with much weaker input. Okay, this is the main obstacle we had to go to overcome. Okay, so with this I will end, and thank you.
Question?
Yeah, so in the case where you have free products of finite groups, do you have a nice rational function for this expected number of fixed points?
Yeah, so it's basically for finite products of free groups. If you look again at uniform, it's a bit easier than surface groups, but basically I would say the main obstacle was the same main obstacle here, and once we have made this method more flexible, then it was done also for products of finite groups, free products of finite groups by Jezelnik and It's a good question. So there are ways to get some information about spacing of eigenvalues from not with this method, not with the polynomial method, but from these results, which there are some. I don't know the details though, but I can provide you some references. Paper by No and by Maoz.
What may be closer to this is, suppose you have that the universal, the regular representation has two bands. And now this strong convergence was for the outliers there, but you could probably do the outliers which are in the middle also. Not spacing, I'm talking about...
No, but I think strong convergence gives you that for free. I mean, if you know strong convergence...
I'm saying this, to answer his question, I mean, where most of the eigenvalues lie, that's Buchalescu, that's easy. Now you're saying that anything outside where the most of them lie, you can still control.
Right. And strong convergence also gives you, so in some cases, like in always bipartite graphs, in the bipartite tree, you get, even for graphs, right, you have, you don't have the whole spectrum, but strong convergence you can get from it, you can deduce from it also that you don't see eigenvalues there as well. So, but I know this is probably not what you asked, but...
Now, I think the interior spacing, if that's what you're talking about, that's much, much harder. Because this is at the scale, this is at the edges of the spectrum. To get in the middle, to get...
Yeah.
Say,
No, but there are some, I mean, Rudnick had some results about this, and...
yeah, but they... yeah, we can discuss it.
Let's thank Doron again.